Students, hope you are doing well. Today I'm going to start a new chapter, chapter 3, that is electrochemistry. So to start with, what is meant by electrochemistry? Here electro stands for electricity. And chemistry is chemical reaction. Or we can also say electrical energy. And chemical reaction, we can say chemical energy. So, electrochemistry is the branch of chemistry where we study the conversion of electrical energy into chemical energy or chemical energy into electrical energy. So, based on whether we are going to convert electrical energy into chemical energy or chemical energy into electrical energy, there are two types of devices. That is electrochemical and electrolytic. In electrochemical device, we convert chemical energy into electrical energy. Whereas in electrolytic device, we convert electrical energy into chemical energy. So in this chapter, we are going to study about electrochemical device in detail. Electrochemical device, or we can say electrochemical cell. So let us see what is an electrochemical cell with the help of an example. In order to understand electrochemical cell, first you have to know redox reaction. I'm sure most of you know what is redox reaction. RED, red stands for reduction. Whereas OX stands for oxidation. So the reaction where both reduction and oxidation takes place is known as redox reaction. So for an electrochemical cell, you need to have a redox reaction, okay? So if you want to define electrochemical cell, it is a device which converts chemical energy of a redox reaction into electrical energy. The most common form of electrochemical cell is galvanic cell. So let us see what is galvanic cell. Electrochemical cell, it consists of two half cells. That means the oxidation and the reduction takes place in two different electrochemical cells. So let us take this redox reaction Zn, zinc solid, plus Cu2 positive, which is aqueous, gives Zn2 positive, which is aqueous, plus Cu solid. In this electrochemical cell, we'll take zinc electrode. And here, we'll take copper electrode. And is connected to a battery. Now, here we have anode, and at anode, oxidation reaction will take place. Whereas on the right hand side, you have cathode, and at cathode, reduction will take place. So this is zinc electrode, this is copper electrode. Now, in this half cell, you also need an electrolytic solution. So if you take zinc electrode, the electrolytic solution is a salt of zinc. So we'll take an electrolytic solution of zinc sulfate. In the other half cell, since we have taken copper electrode, the electrolytic solution is made up of copper sulfate. Now we know from physics, in order to complete this cell, that is, for the flow of current, you need a closed circuit, a complete circuit. Now, these two half cells will be completed with the help of salt bridge. This salt bridge will help us in the flow of electron from anode half cell to the cathode half cell. So you can say there are two half cells, anode half cell and cathode half cell. Anode half cell is also known as oxidation half cell. Why? Because at anode, oxidation will take place. Similarly, at cathode, reduction will take place. So this half cell is also known as reduction half cell. So when the reaction starts at anode, zinc will undergo oxidation. That means zinc solid will release two electrons and will form a zinc ion. So zinc from here will go into the solution, will release two electrons and remain as zinc 2 positive in the solution. The two electrons released at anode will go to the cathode with the help of the salt bridge. So the salt bridge will help in the flow of electron from anode to cathode. So at cathode, the copper ion present in the solution will receive two electrons which comes from the anode and is reduced to copper. And this copper will go and get deposited at the electron. So at cathode, the reaction is Cu2 positive, aqueous, will accept two electrons and will form Cus. Now if you combine the anode half cell reaction and the cathode half cell reaction, we'll get the overall reaction of this electrochemical cell. This electrochemical cell is known as Daniell cell. Wherever you take zinc as anode, copper as cathode, the combination of these two is known as Daniell cell. Next, standard electron potential. if you consider an electrochemical cell, you have two half cells, that is anode half cell and cathode half cell, or oxidation half cell and reduction half cell. So standard electrode potential is the difference between the two half cells. That is, anode cell is equal to anode cathode minus anode anode. Is also written as anode R minus anode L. Now, if you see the electrochemical cell, you'll find the anode is always placed on the left hand side and cathode on the right hand side. So instead of writing anode cathode minus anode anode, we can also write anode R, that is on right hand side, minus anode L, that is on left hand side. Next, let us say cell representation. We'll see how to represent a cell, that is an electrochemical cell. So in order to understand the cell representation, let us take a cell reaction. We will take overall reaction. Let us take the Daniell cell. ZnS, that is solid, plus Cu2 positive aqueous will give Zn2 positive aqueous plus Cu solid. Now we can easily find out the oxidation and reduction from here. You can see zinc, the oxidation number is 0. Here the oxidation number is 2 positive. So we know when the oxidation number increases, it means oxidation. So this is oxidation. Copper 2 positive. So oxidation number is 2 positive. Here is 0. So 2 positive to 0, oxidation number decreases, it means it's reduction. So oxidation half cell or anode half cell. So oxidation half cell reaction is zinc to zinc 2 positive. So to balance this, we'll add 2 electrons here. Reduction half cell, Cu2 positive, aqueous to Cu solid. So to balance it, we'll add 2 electrons here. Now, in the cell representation, we'll first write the oxidation half cell, followed by salt bridge, and then it's followed by reduction half cell. So the oxidation is zinc to zinc 2 positive. So zinc to zinc 2 positive. Now this represents electron. Then with the help of 2 parallel lines of equal length in a vertical direction represents salt bridge. So this is oxidation, Zn to Zn2 positive, this means electron, salt bridge followed by reduction. And the reduction is Cu2 positive to Cu. So we'll write here Cu2 positive, aqueous to Cus. Now when we represent the cell, we don't have to show the electron. We just have to show the reaction, the oxidation half cell, salt bridge, and the reduction half cell. Next topic is the most important topic in this chapter, that is electrochemistry, and it is Nernst equation. We mostly get numerical based questions from this topic, that is Nernst equation. But first let us see how to write Nernst equation. So for that, we first have to consider a reaction. So Mn positive, M is a metal with N positive charge. So this is metal ion. And it will accept N number of electrons to undergo reduction and will form Ms. So this is a reaction. For this, the Nernst equation is given as E cell is equal to E naught cell minus RT by NF ln of, in numerator you'll write the product concentration. You'll write the concentration of the species present in the product. So Ms. And in denominator you'll write the concentration of the species present in the reactor. So we'll write here concentration of Mn positive, that is aqueous. Now E cell is the electrode potential at a given concentration of electrolyte. Now this is when the concentration is not equal to 1. That means we can change the concentration of the electrolytic solution, and based on that the electrode potential also change. So this is the electrode potential when we change the concentration. That means at a different concentration. E naught cell is standard electrode potential. So this is the electrode potential when the concentration is equal to 1. R is universal gas constant. T is temperature. N is number of electrons. Number of electrons means the number of electrons which takes part in the reaction. So you can see here for this reaction you have N number of electrons, that's why we'll write N here. F is Faraday's constant. So this is how we write the Nernst equation. And here E naught cell is equal to E naught cathode minus E naught anode. Now let us try to put the value of RT and F and modify this equation. So we have this equation, E cell equal to E naught cell minus RT by NF ln of Ms by Mn positive aqueous. Now at 25 degrees centigrade, or you can say 298 Kelvin. Most of the time the numerical, the questions are asked at 298 Kelvin. So if the question is asked at 298 Kelvin, instead of using this equation, you can use the modified equation. So if the temperature is 298 Kelvin, that is T equal to 298 Kelvin. Our universal gas constant is 8.314 joule per mole per Kelvin. N is number of electrons. F is Faraday's constant. So F equal to 96500 coulomb per mole. So if you put these values here in this equation and simplify, so we'll get E cell equal to E naught cell minus R value is 8.314, T is 298 Kelvin, N is number of electron, F is Faraday's constant, it is 96500. And we know the relation between ln and log is ln equal to 2.303 log. So we can write here 2.303 log of ms by m and positive aqueous. Now if you simplify this, you'll get a value of 0.0591 by n. So if you simplify this part, you'll get 0.0591. So instead of using this equation, putting the value of R, T, F and trying to simplify it, you can use this equation. It will save time and it will be easier for you to calculate the answer. Log of. Now, if the species metal ion, if it is in solid state, that means pure, concentration is equal to 1. So instead of writing ms, we can write here 1 by m and positive aqueous. So this is equal to E cell equal to E naught cell minus 0.0591 by n log of 1 by m and positive aqueous. Next, let us try to write the Nernst equation for Daniell cell. So let us take this equation, Zn S plus Cu 2 positive aqueous will give Zn 2 positive aqueous plus CuS. Now the Nernst equation for this reaction, that is Daniell cell reaction, is given as E cell equal to E naught cell minus RT by NF ln of, in numerator you write the species present in the product side, so concentration of Zn 2 positive aqueous, concentration of CuS. In denominator you write the concentration of the species present in the reactant, so Zns Cu2 positive aqueous. Now we know the concentration of species in the pure state, that means without any oxidation state, is equal to 1. So we can write from here concentration of CuS is equal to 1, concentration of Zns is equal to 1. So E cell is equal to E naught cell minus RT by NF ln of, in numerator you'll have concentration of Zn2 positive aqueous multiplied by 1. In denominator you'll have concentration of Cu2 positive aqueous multiplied by 1. So you'll have concentration of Zn2 positive aqueous, denominator concentration of Cu2 positive aqueous. Now if you consider this at 298 Kelvin, we know at 298 Kelvin R is 8.314 joule per mole per Kelvin, F is 96500 coulomb per mole, and here the number of electron is equal to 2, because zinc will release 2 electrons when it undergoes oxidation, and the same 2 electrons are used by Cu2 positive to undergo reduction. So in the reaction, the total number of electrons which involved is equal to 2. So we can write from here E cell is equal to E naught cell minus ln, if you convert in log, is 2.303, R is 8.314, T is 298, 2 multiplied by 96500. Log of concentration of Zn2 positive aqueous by concentration of Cu2 positive aqueous. If we simplify this part, the value is equal to 0.0591. So E cell is equal to E naught cell minus 0.0591 by 2 log of concentration of Zn2 positive aqueous by concentration of Cu2 positive aqueous. So this is how we write the Nernst equation for Daniell cell. Next, let us see how to write the Nernst equation for a reaction which is represented as AA plus BB gives CC plus DD, where AB, capital A and capital B represents reactant, small letter A represents the stoichiometric coefficient of A, small letter B represents the stoichiometric coefficient of B, C and D are products. Small letter C represents the stoichiometric coefficient of C. Small letter D represents the stoichiometric coefficient of D. So for this, the Nernst equation is written as E cell is equal to E naught cell minus 0.0591 by N log of, in numerator you'll write the concentration of product, that is concentration of C, multiplied by concentration of D. In denominator you'll write the concentration of reactants, that is concentration of A, multiplied by concentration of B. Now if we have a certain stoichiometric coefficient, it is raised to the power. So if we have C stoichiometric coefficient, it will be concentration of C to the power C. If you have D concentration, D stoichiometric coefficient, so D concentration power D. Similarly, A concentration power A, B concentration power B. So this is how we write Nernst equation for the reactions with certain stoichiometric coefficient. So we have learned how to write the Nernst equation. In the next video, we'll study some numerical problems from this topic. Thank you.